Welcome back, ELE 112 students. Today's lecture centers around Chapter 8, Section 5, Thevenins Theorem. This is the second video, known as Thevenins Theorem number 1. We're going to go through the steps and exactly what a Thevenin theorem is. This came straight out of your book. Way up there at the top at figure 8-30, this is the general form of a Thevenin circuit. This looks like a chapter 3 problem with one resistor, one power supply. That is what a Thevenin series circuit looks like. The reason why Thevenins is such a great theorem for difficult problems that must be repeated multiple times is because the final circuit literally boils down to a battery and a resistor or an impedance in later chapters. So keep in mind what that looks like. As far as the things we're looking for, we need to figure out how to solve for V Thevenin and how to solve for R Thevenin. There's a technique involved. Excuse me. And we will be learning that technique. In the bold in the middle of your page, it says, the Thevenin equivalent voltage, V Thevenin, is the open circuit, no load voltage between two terminals in a circuit. What's important to note is this is in the original circuit. So you've got this big circuit and there's a load resistor somewhere. You have to literally remove the load resistor in the Thevenin voltage step and go find what voltage floats to the gap when you disconnect this part. That will be the battery that the resistor is seeing in the Thevenin circuit. The second part of Thevenin's circuit reduction technique involves finding the resistance that the load which you've removed, what resistance does it see? Looking back into this complex circuit, you've got to remember there could be 5, 10, 15 components. There could be resistors, capacitors, inductors later on. And there's also a power supply in the way. And that power supply has resistance. That power supply has impedance. From earlier material in Chapter 8, you learned that a battery is a dead short, theoretically, and we will be using that to our advantage. And we learned that a current source is an open circuit, in other words, infinite resistance, and we will use that to our advantage as well when we are solving these circuits for Thevenin voltages and Thevenin resistance. So the second bold statement there says the Thevenin equivalent resistance, R Thevenin, is the total resistance appearing between the two terminals in a given circuit with all the sources replaced by their internal resistances. So, to summarize, a power supply has 0 ohms. Theoretically, in a perfect world, of resistance, while a current source has infinite resistance. We will use this moving forward. It's important that you make some notes during this video. Go back and play it a few times because you're going to need some of this information moving forward. Now, the last blue statement's very important. I've said it before in the first video, I believe, but I'll say it again here. Read what it says. Although a Thevenin equivalent circuit is not the same as the original circuit, it can't be. It has tons of parts less in it, but it acts the same to this one part that you're analyzing. It acts the same in terms of voltage and current as the circuit with more parts in it. That takes a little while to grasp over. here's a picture of what we're talking about. This is straight out of your book. There's an original circuit here circled in black, and there could be 1,000 parts sitting in there. And here's this little sheep resistor sitting over here, the load. And it just sits out there, and the only thing that load can do is receive current and develop voltage drop. That's all it can do. It doesn't know how that circuit is built. The analogy would be, I've got a 5-gallon water bucket, and I'm filling it with 1 drop at a time, and that takes forever, and the bucket fills. Or I fill the bucket with 1 drop the size of the 5-gallon bucket. It fills quicker, but the bucket still has water in it, you see? So here's this lonesome resistor circled in red, and when it's connected to that complicated circuit, it feels voltage there, and it feels current that's developed by the voltage that it is introduced to at that point. Now, the second circuit down below in green is the Thevenin's equivalent circuit, and we saw that was just a battery and a resistor. There's not much to that, but what is it that we're supplying this load over here on the output? We're supplying a current and a voltage to that resistor, and he doesn't care where it came from. So if we can take the complicated circuit in black up above, and well, it's not in black anymore. If we can take this complicated circuit in black up at the top and characterize exactly what voltage is going to be out here at the terminal and how much current is going to flow into this load that's circled in red, then we could build a simpler circuit called the Thevenin circuit, which would be like almost like a surrogate circuit that would provide the same current and the same voltage. And this would be useful in solving the circuit for that load if I wanted to change it multiple times. Okay, so here is the actual steps involved in solving a Thevenin circuit. I want to make a note here. Order is not important. What I mean by that is that you're going to be solving for V Thevenin and you're going to be solving for R Thevenin. And it doesn't matter if you go find R Thevenin first and then go find V Thevenin, or vice versa. It is totally irrelevant. They are two different processes. One could be easier or harder than the next, but it is solvable in any sequence you want. You just have to implement the steps the right way. Okay, so if you take a look at this came straight out of your book. The summarizing steps are as follows. And the first thing they do here is come through and ask you to find the Thevenin voltage, but you know that you don't need to. You could go to step 3 first and find R Thevenin. So the first bullet says, open the 2 terminals. Remove any load between which you want to find the Thevenin equivalent circuit. So every time you do one of these problems in this chapter, they're going to tell you where the load is. You have to know where the load is, otherwise you have nothing to do. Number 2 step, using old-fashioned and any technique in the book that works, determine the voltage across the terminals when you remove that load. You'll remember that in some cases when you remove a resistor, new voltage shows up at that spot, so to speak. When you remove a resistor from a location, let's say it's a 1K resistor, when you remove it, that 1K resistor changes to infinite resistance at that location, and a voltage will form there. That is what we're going to be solving for. It will become cleaner and clearer when we practice a few problems. Number 3 step, now that we've gotten the voltage that floats to the opening, determine the resistance, which is called R Thevenin, between the two open terminals, with all the sources replaced with their internal resistances. Voltage sources shorted, current sources opened. Next step. You've actually finished the Thevenizing of the circuit, but the next step says connect your Thevenin circuit in series to produce a complete Thevenin equivalent for the original circuit. So build your circuit. Place the load removed from step 1 across the terminals, and now you can calculate using simple Ohm's law analysis, the current and the voltage that goes through your load. In future videos, we will work some sample problems. Thank you for listening.